Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Gabe Cohn doesn't really require that much introduction. He's been around for a while, hanging out with us. I still remember first meeting with Gabe, young superstar student out of Caltech, coming out, specialized in embedded systems, VLSI, computer architecture. Over the years, it's been great hanging out with Gabe, watching him grow into, take his skill set and grow into an amazing Ubicomp researcher. First internship, Gabe's pushed the boundaries in various ways. I used to have this standing challenge for all my interns to try and break as much as they can in the first week here. Until Gabe came in, Scott Saponis, now with the group, held the record for taking apart our $40,000 EEG device in his first week, and I walked in and he couldn't put it back together. First week in Gabe's internship, he called me. He goes, "Hey, I think I broke your house." So I stopped doing that challenge. Didn't seem like it was easy to top. First internship, Gabe set the bar really high. Ended up with 3 papers, 2 Best Paper awards, 1 Best Paper nomination, which made it really rough on our subsequent interns. If you look at his portfolio, an NSF graduate fellowship, an MSR graduate fellowship, multiple Best Papers, startup company that's gotten funding in its recent Series A round, that's out on market, and that it looks like he's got prototypes of. Rather than stand in the way, let me hand the mic over to Gabe.
All right. Thanks a lot, Desney. So I'm going to talk about a bunch of my work on building embedded sensor systems to bring Ubicomp to life. And since a lot of this work was done here at MSR, you might recognize some of these things. So first, what is Ubicomp? So Ubicomp, or Ubiquitous Computing, is this idea that was started in the late 80s to early 90s by Mark Weiser and his colleagues at Xerox PARC. And the idea was that instead of having users interact with a single personal computer, they would instead interact with multiple computing devices simultaneously as they go about their everyday lives. And these computing devices would not only be sitting on your desktop, as shown here, they would also be worn on the body in the case of wearable computing or mobile computing, or off the body and seamlessly embedded into the user's home and work environments. And in order to enable these kinds of Ubicomp applications, requires building these embedded sensor systems. Now, embedded sensor systems can generally be broken down to 4 main parts. There's the human interface, the sensing, the computation, and the communications. And developing these kinds of systems actually requires expertise in nearly every subdomain of computer science and electrical engineering. Luckily, in the last 25 years, since Weiser had this vision of Ubicomp, we've actually seen exponential growth and improvement in nearly every single one of these subdomains. And as a result of this progress, we've actually seen our first major victory in Ubicomp. And that is that mobile computing truly is ubiquitous today. So from our smartphones and tablets and laptops, we've really become accustomed to having information always available at our fingertips. And although this is a huge success for Ubicomp, we still have not yet realized many of the original dreams of wearable computing and enabling smart environments. However, this is still a really exciting time because we are just beginning to see what these kinds of applications might look like. But in order to bring many of these Ubicomp applications to life, we need to continue to do research, not only in each of these subdomains of computer science and electrical engineering, but research that crosses the traditional boundaries between the human interface, sensing, computation, and communications. And this multidisciplinary research is required in order to reduce the adoption barriers that are currently limiting widespread use. And the problem, as you can see here, is that sensing is still very invasive, both in terms of the number of sensors required on the body and off the body, as well as the way in which these sensors are used. And often the problem is actually power consumption. So the high power consumption of wireless sensor systems typically limits their battery life and therefore their usefulness. And so my work is focused on trying to make sensing more non-invasive by doing tightly integrated hardware-software development with a focus on ultra-low power indirect sensing. More generally, I look at identifying new opportunities for sensing, building new embedded sensor systems, and then finding new application domains for this sensing. And I do this work for both on-body and off-body sensing. And so this slide gives an overview of most of the work I've done in grad school. And in this talk, I'll only talk about a subset of this, so I won't bore you with everything I've done. So I'll talk about a little bit of work that I did here, actually, on-body sensing to enable low-power human-computer interaction by leveraging the conductive properties of the body. And then I'll talk about some off-body sensing, where instead of leveraging the conductive properties of the body, I'll actually leverage the existing infrastructure, again, to reduce the number of sensors required or reduce power consumption. So let me first talk about this on-body work. And so the focus of this work is actually to enable human-computer interaction. And so as we move to more ubiquitous interfaces, we have to move away from the traditional mouse and keyboard paradigm of interacting with computers and find more natural ways of doing these kinds of interactions. And so one thing that's become very popular is to use whole-body gestures. So this is something we're all very familiar with, using computer vision and depth cameras like the Microsoft Kinect. Now, unfortunately, these camera-based systems actually have some drawbacks. So one is occlusion. They can only see directly what's in front of them, line of sight. So if you have a second user, they might actually block the line of sight path from the camera to the other user. In addition to occlusion, there's big problems with lighting. So anyone who's been upstairs to Andy and Benko's lab sees they all work in the dark. And the reason is because lighting actually is a problem for a lot of these camera-based systems. This is actually from the Kinect support page. And you see confusing things like make sure the room is brightly lit and avoid direct sunlight. But I see actually the biggest issue with camera-based systems is their limited field of view. So if you want to interact using whole-body gestures in your living room, you can do that. You can use a Kinect, and that works great. But if you want to do this kind of interaction everywhere in your house, you'd have to instrument your entire house with cameras. And of course, this is difficult in terms of the installation and maintenance, but it's also not practical to put cameras everywhere in your house. This is still a really interesting way of doing whole-body free space gestures, so I want to do this kind of interaction as well. But I don't want to use a camera, because I don't want to be limited to doing this just in the living room. I want to be able to interact with my computer anywhere. So I could interact in the kitchen, in the dining room, or in the bedroom. And so I'm going to talk about a project called HumAntenna, which allows you to do just this. It senses whole-body free space gestures in real time, but it does it, instead of using a direct sensing approach where you use a camera, it uses an indirect sensing approach, where we actually use the human body as an antenna. And I'll describe what that means in just a minute. But the real advantage of this is that there's no instrumentation to the environment and only minimal instrumentation on the user's body. So you can think about it as Kinect-like gestures without the Kinect. Now, I talked about using the human body as an antenna. So let me describe a little bit about antennas. So you might recognize this. This is a typical TV antenna. It's called a bunny ears antenna because of the way it looks. But it's not the only kind of antenna. This, in addition to being my brother, is also an antenna. This is a human body antenna. It's called a teenager, again, because of the way it looks. But it actually wasn't designed to operate at a fixed frequency, like the TV antenna. It's really just a dielectric with a complex geometry, which works fairly well as an antenna between about 40 hertz and 400 megahertz. And this is nothing new. This is actually known as the body antenna effect. And it's actually a source of noise and interference in body area networks and anyone who's looked at analyzing signals on the body, so ECG, EMG, like a lot of the people here have done. And so in this project, I'm actually going to use this noise or this interference as my signal. So let me show you how this works. Here's Bongshin in cartoon form. This is, I think, the only embarrassing picture of anyone I have in this room in this slide deck, I just realized. And so here's our human body antenna. And in this project, we're going to look at frequencies below about 200 kilohertz. And in this band, the signals that the body picks up are the electromagnetic noise radiating off the power lines and appliances in the home. And so we can actually sense this very simply just by measuring the voltage on the body and then applying some signal processing and machine learning in order to enable this gesture interface. So what does this signal look like? Well, if you take a look at it in the time domain, you see basically a distorted sine wave. at 60 hertz. This makes sense. 60 hertz is the frequency that power is delivered to all of our appliances. So this is that noise that's radiating off the power lines. The amplitude of this signal actually varies as a function of the user's proximity to these noise sources, to the power lines and appliances. If you look at this in the frequency domain, you again see the 60 hertz peak, and then you see all the harmonics of 60 hertz. Now, the harmonic amplitudes vary as a function of the user's posture. And this is because as the user changes their posture, they're changing their antenna properties. So essentially, the transfer function of that antenna is changing. So using a machine learning approach where we pull out some of these time and frequency domain features, we can actually train the system with the user in a number of different postures and then classify which postures they're in. If we look at higher frequencies, up to about 200 kilohertz, we notice there's these peaks. And these peaks are the noise generated by the switch mode power supplies, all these power bricks that we have plugged in all over the place. And again, the amplitude of these peaks is a function of the user's proximity to those noise sources, to the appliances that generate them. So again, using a machine learning approach and taking these features as well, we can also determine the user's location. So this is really exciting. With no instrumentation to the environment, just looking at the voltage on the body and applying some signal processing and machine learning, we can determine the user's posture and location. Of course, I promise more than just posture and location. I said we can do whole body gestures. So by gestures, I mean the user is actually moving, not just standing still. So let's take a look at what the signal looks like when the user moves. So you get this voltage waveform like this. The first thing we want to do is actually segment when the user is actually moving. So to do this, we'll take a low-pass filter at about 10 hertz, and we'll notice something really interesting. So if you look at this green curve, you see that when the user is not moving, the line is pretty stable around 0 volts. When the user moves, it deviates away from 0 volts. So for now, I'm going to ignore why that's happening. I'll come back to that in a few minutes. But we're going to use this for segmentation. So we can simply set a threshold on this green curve and figure out when the user is moving. The next step is we want to do some feature extraction, determine, pull out some features to use for classification. So we'll take a high-pass filter at 40 hertz. And here we can see the AC amplitude of this voltage signal on the body. And you can see that during the gesture, this amplitude changes. So in order to capture the dynamic nature of the gesture, we'll actually divide their segmented gesture into 7 feature windows. And over each window, we'll use a number of time and frequency domain features, and then use all these features in a support vector machine classifier. And this will allow us to classify between a number of pre-trained gestures. So in the evaluation I'm about to show, which many of you went around homes and did many times, we used 12 pre-trained gestures. So this involves things like waving your arms, moving your body from side to side, and then series of punches and kicks, because we're comparing to Kinect, so we have to do a bunch of punches and kicks. And so we did an evaluation with 8 participants in 8 homes, and found this actually works with about 93% accuracy. So again, this is really exciting. There's no instrumentation in the environment. Just looking at the voltage on the body, using signal processing and machine learning, we can determine what kind of gestures the user is doing with 93% accuracy. Yeah? You have to train per person per location to get this level of accuracy. You could potentially make a model that works regardless of person. We only had 12 people or 8 people, and so we definitely got much better than chance with that. But with 8 people, we can't really answer the question of whether it will work in general.
Does it drift overnight?
So because we're using the noise in the environment, it's definitely going to change as the noise changes over time, right? So if you change the setting of the lights or turn on a new appliance, then the noise around will change. And so, yes, how well it works will change over time. Depending on the features you choose, you could actually choose features that are more or less sensitive to that. Yeah?
Did you attempt to correlate the performance envelope for the gestures so people are inconsistent?
We didn't in here, but that's actually kind of an interesting thing to do. And it depends, on the gestures and how they're confused. So what's actually interesting is what's confused most is not kind of slight variations of the same gesture, but things that are symmetric but completely opposite. So, moving your right hand versus your left hand. And the reason for this is we can really only tell that apart if something about the noise, is different on one side versus the other. So that's actually more of the issue. But it totally depends on the noise environment.
Okay.
Yeah.
So if I go to an environment that's trained by other people, like I got my model for my house, say AJ has her model, and in her house I happen to go there. Is anything reusable from those two sets and two sets of features?
So what I think, and this is kind of just speculation because we haven't done that exact test, but I would say that if AJ has her trained set and you go to her house, you could use her model and it won't work as accurately as if you had trained it yourself. But you could maybe use that as a starting point and then bootstrap to kind of build a personalized model. So I think you can definitely have location-based models that are people agnostic. There will be some differences on different people, particularly if they're different sizes, right? So it might work fairly well because you and AJ are about the same size, but AJ and AJ's kids might not work quite nearly as well. Yeah, Benko.
Varying with how your body is hydrated?
I think somebody is looking ahead in the slides. So, we didn't control for how people were hydrated. I wouldn't expect that to change much. I would actually expect the humidity in the room to matter more than how well hydrated you are. Mostly because the frequencies we're looking at. The body is pretty much a conductor at 60 hertz or so. All right. Any other questions? All right. Well, so let me show you a real-time implementation of this. So here's a video. I'm going to perform a gesture, and the TV will then show you which gesture I performed. So unlike Connect, it's not building the skeletal model in real time. There's actually 12 pre-recorded stick figure videos in here. It's going through the whole process that I told you and determining which of these 12 gestures I'm performing. So I went to this location, did each gesture once as training, and then filmed this video. So as you can see, there's no instrumentation on the environment and just this simple training. Now, one of the interesting things about this is we can get away from some of the problems that existing camera systems have. So for example, I can turn around, as I'm about to do, perform the same gesture, and it will still work because we don't actually have this occlusion problem. Yeah?
So I assume that the purse you're wearing contains the sensors that are on you, and you talked about how like battery power was one of the problems with sensing. I don't see any wires, so I assume that that's battery power. So does this have that same
It's a wire on the shoulder.
challenge?
So I've never heard someone called a purse, but let me explain what's in the shoulder bag. So what's in the shoulder bag is basic. So you can actually, someone mentioned there's a wire. So there's actually a wire going to the back of my neck. So I need contact with the body. Here I'm making contact with the back of the neck. It doesn't need to be the back of the neck. We really wanted a location that isn't going to move around as I do gestures, so there's no confounds. But it could be on your wrist as well, or anywhere else. In the bag is basically just an analog digital converter. So digitizing the signal that's on the body, and then there's a wireless transmitter sending it off to our server. It doesn't need to be a large bag. You could simply, reduce this into like a small wristwatch form factor. Power consumption could be a problem depending on how quickly you're sampling and if you're sending a wireless signal. So in this project, I wasn't concerned with power consumption. I'm about to show you on like the next slide what you can do about power consumption, though. Yeah.
How small can you go? Not in terms of the device size, but in terms of the gesture. These are all really large body movements. Can you detect a wave gesture?
So I think the real issue is basically the noise in the environment. So you could train the system with like small finger movements, and that will probably work for some time, but as the noise changes, that will stop working. And so it's really a question of what's the variability in the noise and not necessarily how fine-grained the gestures can be, if that makes sense. So yes, I think you can train a classifier that will work with like some very small gestures, but it won't work very long. If you want it to work robustly over time, you need to use larger gestures. And actually, while we have this, I think an interesting way of making this actually realizable is you combine this with a vision-based system where you actually stand in front of Connect and use that as your training. You perform some actions in front of Connect, you train the system, and then you can walk away, and the system can keep working, perhaps. Now, because there's drift over time, you might have to periodically walk in front of your Connect again to update the model. But I can imagine something like that working. But I do consider it practically to be more, I think you could do waves we actually had waves in our gesture set, but I don't know if you can do like finger motion. Yeah.
Is there an ideal kind of noise that you would consider just plugging into the wall?
Exactly. So, one of the goals here was, what can we do with ambient noise? But, if you really want to make this work and you're willing to put one thing in your wall, what would that noise source look like? And we haven't really explored that, but you can definitely do a lot better if you control the noise. And one of the things you can do is actually get around some of the issues that we have right now with, what happens when someone turns on a light. Well, if you're making your noise, then you don't have to worry about that. So that's an interesting thing to explore. Yeah?
Did it matter if we're on carpet as opposed to some other surface?
So it does matter what your grounding is. And this matters, what shoes you're wearing, and to some degree what the surface you're standing on is. So yeah, that does matter because it's going to affect, the amplitude of the voltages on your body, for example. Yeah?
Also, Ray, since you've mentioned power several times, have you done any work looking at how you can convert sort of human movement or energy into stored power? Since it's all about movement.
Right, so I haven't done any of that work. There's actually been a lot of that work in the community, looking at how do you harvest kind of energy from the motion of people. And it, obviously depends on where on the body you want to harvest this. So the feet are actually really good. There's actually a lot of energy that can be harvested from your feet. Other things don't actually move that much, it turns out. People are learning this when they have Fitbits on now. They actually sit around most of the day, unfortunately. All right, so let me move on. All right, so the one thing I skipped was, I said when the user moves, there's this voltage that deviates away from 0. And I said I'll ignore why that's happening. But let me actually talk about why that's happening. So it's actually not obvious. And I spent about 6 to 8 months trying to figure out what was going on there. And what it turns out is that this is caused by the static electric field between your body and the environment. And this voltage happens as you move and change the static electric field. So it turns out this is useful for more than just segmentation for human antenna. And it actually spawned a whole other research project around static electric field sensing. And the real advantage of this is that it's ultra low power and enables whole body motion sensing. So before I talk about what it means to do static electric field sensing, let me talk about traditional electric field or capacitive sensing. So this is something that's been done for many years in the HCI community. And the idea is you actively produce a time-varying electric field and then sense how that field changes as a function of user activity. And this was done in the mid-90s with a single frequency. More recently, it's been done with swept frequencies. But all of this work, you have to actively produce a time-varying electric field and then sense how that field changes. Static electric field sensing is different in that you passively sense the existing static or DC electric field that already exists between our body and the environment. So I'll try to explain this with this field diagram here. So these red lines represent the electric field. The closer the lines are together, the stronger the field. So it's strongest at the feet because you're really close to the ground. And I'm going to represent the environment around the user as ground. So if I put a sensor on the user's wrist, there's two new electric fields here. There's one between this local ground plane that's on the sensor and the body, and between that local ground plane and the environment. So I can represent this with a simple 3-capacitor model to represent the capacitive coupling between all these nodes. So there's the capacitive coupling between the body and this local ground plane, between the local ground plane and the environment, and between the body and the environment. Now if I measure the voltage between the body and this local ground plane, I can see that it's a function of the charge on both sides as well as the capacitive coupling on both sides to the environment. Now this is interesting because if the user, for example, lifts their leg, they're going to change that capacitive coupling, which is this parameter CB, and therefore this voltage will change. So essentially there's changes in this voltage whenever the user moves. And so this is a really easy way, a low power way of sensing whole body motion. And kind of the nice thing about this is the hardware is quite simple and therefore can be made very low power. So we need contact to the body. some gain stage, and then a low-pass filter. Now, the reason we have a low-pass filter is because we know from human antenna that there's signals at 60 hertz and all the harmonics. We want to filter all that out. We're only really interested in this very low frequency signal, less than about 10 hertz. And so I built this into a wristwatch form factor, which I can pass this one around. And we began to explore like how is this useful? And so I'm going to show you a video in which we actually compare it to an accelerometer. I can give you data that's very similar to that of an accelerometer. So in the background here, you're going to see the top trace is the output of the static electric field sensor, and the bottom 3 traces are the 3 axes of an accelerometer. And what you'll notice is as I move my wrist, you see the sinusoidal wave pattern on both the static electric field sensor as well as the accelerometer traces. So it can't give you the fidelity of data that an accelerometer can, and that it can't tell you, your motion in 3 axes. It can't give this in real units of acceleration, but it can give you some of the same kinds of data about how much you're moving and maybe where you're moving. And so one of the real advantages why you might use this over an accelerometer is power consumption. So this is plotted on a log scale. And you'll see that the static electric field sensing device is actually about 2 orders of magnitude, or 100 times lower power than some of the best commercial accelerometers for this application of sensing human body motion. And it's even an order of magnitude lower power than the best research accelerometers right now. And what's even more impressive is that this was built just using off-the-shelf discrete analog components. If you were to make an integrated circuit like is done for these accelerometers, you could bring that power consumption down another 2 to 3 orders of magnitude. Yeah.
One quick one. So I see all your demos are in front of the big TV, right, and in environments where there are, likely to be strong electric fields. Mm-hmm. If you go off into the middle of a wet field barefoot, right, do you think this will work?
I did just that. I went into, I wasn't barefoot, I guess, but it was a wet field. It's 60 acres over in Redmond. I went to the middle of the field, and there's no power lines anywhere around. You don't see 60 hertz there. You're far enough from the power lines, but you do still see the static electric field sensing signal. So basically this is happening because your body and the environment are some different potential. So there's going to be some field, and you're just sensing changes in that field. So it'll actually work regardless of the environment. I also did some interesting experiments, in screen rooms and anechoic chambers, and trying to suspend myself from the air. Desney has videos of me hanging from the ceiling, trying to test, what matters. Is it your grounding? Is it, the environment? And it actually doesn't matter. It's always there.
Do you think barefoot would not matter?
So barefoot will change things, and that'll change the amplitude, right? If you're still gonna be at slightly different potential. If you would truly have, an ohmic contact at ground, then yes, you won't see much. That's a little difficult to produce. But yeah, the amplitudes are significantly less if you're barefoot than if you have shoes on, as you'd expect. Yeah?
I think these numbers may be a little misleading. So when you integrate it into a sensor, it's not the accelerometer or these sensors that dominates the energy consumption. Right? It's the radio, the microcontroller, and everything else. Mm-hmm. So optimizing this part to like 3 order of magnitude cheaper may not give you much to the end device benefits.
So it depends on the application. I'll actually, in a few slides, show you a use case where this actually has an advantage. So you can ask again in a few slides if you're still confused. But let me move on. So one of the other advantages, in addition to giving data that's similar to an accelerometer, is it can also give you data that an accelerometer just can't. So for example, if you wanted to use an accelerometer to measure not just how much my arm is moving, but how much each limb is moving, right now you'd have to use a number of accelerometers. And this can be rather cumbersome. So with a static electric field sensor, you can actually do this from a single device. So here I'm going to show you another video, and I'm going to hold my arm steady, but move my leg. So of course, my arm is held steady, so you'll notice the accelerometer sees nothing. The static electric field sensor still sees this strong signal, because I'm still going to change the capacitive coupling between my body and the environment. And to answer your question, the reason this might be useful is actually to use it in combination with other sensors like accelerometers that people have begun using for activity recognition, and to use it for ultra-low power wake-up. So you can imagine you're using your accelerometers for some application, activity recognition or whatever, and you want to turn them off to save power when the user's not moving, but you don't know when to turn them back on. And so you could use this sensor and do the threshold in hardware with 2 comparators, and this whole thing to generate this wake-up signal. And this whole thing consumes only 6.6 microwatts, so about the same power as a microcontroller in sleep. Yeah.
So just for comparison again, with the static field sensor, do you always require the machine learning training session for it to understand what's moving?
No, so I actually haven't talked at all in this project about machine learning. So I actually don't have this in the slides, but I actually did say, all right, if we're going to use machine learning, can we classify different types of activity? And you can, course different types of activities. So, no motion versus maybe hand and finger motion versus arm motion, then whole body motion like walking. And you can do that with machine learning relatively simply. What I was saying is you can actually forget about the machine learning. You can actually use this as, for some of the same applications. People are using the Fitbit and Nike Fuel Band just as a pedometer. And you can do that here without machine learning. Yeah. Oh, no? Okay. All right. All right, so let's move on. So I talked about some of these on-body applications in which I'm going to leverage the conductive properties of the body in order to either reduce the number of sensors required to enable human-computer interaction or to reduce power consumption. And now let me talk about some off-body sensing in which instead of leveraging the conductive properties of the body, I'm going to leverage the existing infrastructure in the environment. And I'm first going to talk about a project called GasSense, which is actually the first thing I did in grad school. And the point of GasSense was to measure the gas consumption at the device level. So this is in your home, all your appliances that consume gas, which ones are consuming gas and how much gas are they consuming. Now the reason you might care about gas consumption is actually gas consumption is quite important. So there's been a big focus lately on electricity monitoring, and people have developed ways of doing this kind of disaggregated sensing for electricity. But it turns out that if you actually look at the average home, the majority of the energy is consumed in natural gas and not in electricity. So just like electricity, we want to get gas consumption at this device level. So just like the human-computer interaction work, there are direct sensing ways of doing this. You could actually put an inline gas sensor on each of your appliances that consume gas. There's a few problems with this. If you have a lot of appliances, it could be difficult to install all of these. But the real issue is we want something that the end user can install. And you can't have the end user running around their house cutting into gas lines. It's really just not safe. And so we need to find a more indirect way of sensing this. And so we're going to utilize the existing infrastructure, take advantage of the fact that all these gas appliances are connected to each other on this gas line. So if we sense something about the gas line, we can figure out what's going on at the endpoints. Now, we still have this problem that we can't just cut into the gas main. That's even more dangerous. So we need to, again, take an indirect sensing approach. And so the approach is to actually look at your gas meter. So if you ever walked around the side of your house and walked by the gas meter, you may have noticed that it makes a sound. A residential one makes a hissing sound, and a commercial one makes somewhat of a low roar. And so I realized there was a sound, and I studied what was going on. So it turns out the sound is produced by this disc here. That's your gas regulator. And let me describe briefly how it works. So this is a cutaway of the regulator. So gas flows through this pipe. And as it does, a sound is produced by this large resonant chamber. So this is similar to blowing through a whistle. As you blow air across the top of a whistle, a sound is produced by that resonant chamber below. And what's nice about this is the amplitude of the tone that's produced is a function of the flow of gas. It's actually a linear function of the flow of gas. And so we can pretty easily sense this simply by putting a microphone outside the gas regulator. So similar to some of my other work, and I'm going to go through this pretty quickly, this is a noisy signal. We're going to need to use some signal processing to figure out, to pull out the signal we want. So this is a spectrogram with frequency on the y-axis, time on the x-axis, and the color encodes the amplitude of the audio data. And you'll notice there's lots of noise sources here. So we have cars driving by, wind noise, even an airplane flying overhead. And what we care about is just the signal right here that's produced by the regulator when gas flows. So we can filter some of the signal out, and then apply some machine learning again to determine when each gas appliance turns on and off. And we actually show that you can do this with about 95% accuracy to determine which gas appliances are being turned on and off at what times. So I went through this really quickly because it's using a lot of the same signal processing and machine learning techniques that I used with human antenna. But the idea is that instead of leveraging the conductive properties of the body, we're going to leverage the existing infrastructure in the home in order to enable, in this case, disaggregated gas consumption. Now, this technique is quite nice in that we can get a lot of information about what's going on in the gas infrastructure by putting a single sensor somewhere on the infrastructure. The problem is we can't always rely on this technique. But for everything we want to sense in the home, we can't always take advantage of existing infrastructure. So sometimes we actually have to put sensors everywhere, use what's called distributed sensing. And for this, people typically use wireless sensor networks. So imagine, for example, you want to know the temperature in every room across your house. So the best way to do this is to put a temperature sensor in each room across your house. So let's say this is your house, and you're going to put these sensors all over the place. So you'll typically make these things wireless and have them communicate their data back to this base station receiver. Now, people do this because it's really easy to deploy. You put the sensors out there, you turn them on, the system works. The problem is it's really hard to maintain. And the reason it's hard to maintain is because all of these wireless sensor nodes have batteries. And for any decent size deployment, the vast majority of time and resources are spent replacing batteries. So we really want to reduce the power consumption so these batteries last longer. Unfortunately, there's this well-known trade-off between the power consumption and the range of a wireless system. So imagine this is your home, and you put this base station receiver in the center of the home. And you're going to put a sensor node in this corner bedroom here. So you can turn it on at high power. The signal will make it to the base station, but your battery won't last very long. If you want your battery to last longer, you can turn down the power consumption, and now your battery will last a lot longer, but the signal won't make it all the way to the receiver. So your network is broken. So there's this trade-off between power consumption and range. And so any wireless sensor network kind of tries to find the sweet spot in this trade-off. So I'm going to present a project called Snoopy, which actually finds a workaround that doesn't have to deal with this trade-off between range and power. And Snoopy is actually an acronym which stands for Sensor Network Utilizing Powerline Infrastructure. And it's an ultra-low power, general-purpose wireless sensor network. And unlike existing wireless sensor networks, and similar to some of my previous work, it actually utilizes the power line infrastructure. Not the gas lines in this case, but the power lines. And it uses a technique called power line coupling, in which the receiver is actually plugged directly into your wall, into the power lines, and uses the power line infrastructure as a giant receiving antenna. And so your sensors, your wireless sensor nodes, can still be wireless, and you can put them anywhere, but instead of sending their data wirelessly over the air all the way to the base station receiver, they wirelessly couple to the nearest power line, and the signal moves through the power line to the receiver. So let me show this graphically. So again, we're going to put this base station receiver in the center of the home, but it no longer has those two little antennas on top. Now we're going to plug it into the power line infrastructure and use all the power lines in the home as a giant receiving antenna. So again, if we put this sensor node in the corner bedroom, we can turn it on at very low power. Not nearly enough power to reach all the way over there to the base station, but enough power to couple its signal onto the wireless infrastructure, and the signal will move through the power lines to the receiver. So in this way, you can put sensor nodes all over the home and have them all communicate to this base station in this star network topology. Now, the reason you might do this is that you still get whole building range because power lines go everywhere in the building, but you can dramatically reduce the power consumption at each sensor node because its wireless range is now much shorter. So here I'm doing a comparison between the first research version of Snoopy and existing sensor nodes, including Zigbee and Bluetooth nodes. And again, this is on a log scale. And the first thing that you notice is that the total power consumption of the Snoopy system is about an order of magnitude lower power than the existing nodes. What's even more interesting is that the communication power, the power consumed by the radio, is about 2 orders of magnitude lower power than existing sensor nodes. And one of the reasons for this is that we're using this power line coupling technique. But the other reason is that we're taking advantage of an asymmetric network. So these sensor nodes are transmit only. They can't receive. And so we can push all the complexity of the network to the receive side. And this way we can produce simple, low-cost, and ultra-low power sensor nodes at the expense of a single complex base station receiver. Now there's a number of advantages of this in terms of power and simplicity, but also a number of disadvantages in terms of the reliability and the robustness of the network. So one, there's no receiver on the node, but this means we can't get acknowledgments. The node will never know if the data has made it to the receiver. There's also no coordination between the nodes, so no synchronization, no scheduling, no routing. But also, if the data doesn't make it, it can't automatically retransmit because it doesn't know the data didn't make it. On the plus side, there's no overhead to do all this coordination. But there's 2 big problems here. One is that we don't know that our data makes it to the base station, and if it doesn't make it, we don't know to retransmit. So to address this, we use multiple retransmissions for important data. So if the data is important that it makes it, we'll transmit it multiple times. And we'll use forward error correction, again, to increase the probability that the data makes it. So we'll never know for sure that the data has arrived at the receiver, but we can actually achieve an arbitrary level of reliability via statistical proof. Now, using this power line coupling channel also has a number of advantages in that it's actually very complementary to existing wireless systems. So an existing over-the-air wireless system actually works best in an open field where there's nothing around to attenuate the signal. In an indoor setting, this means it works best in the center of a large room. This is actually the location that Snoopy works the worst because it's farthest from power lines. But if you take a scenario where you want to put a sensor, for example, under a large appliance like a refrigerator, or maybe even inside the refrigerator, over-the-air wireless systems don't work very well because they're inside a metal box or underneath a metal box. This is actually the location that Snoopy works the best because it's right next to a large appliance that's plugged into the power line. So in that way, they're very complementary. But this new power line coupling channel is unexplored. So there's a lot of questions that come up in terms of how do you design and build a system that works in this way that's partially wireless and partially using the power line as a transmission line. So my thesis is focused a lot on trying to explore this channel. So I did a lot of background noise and interference measurements around homes around Seattle. Actually, I didn't bug you guys about this, but these are other people I know in Seattle. And did a lot of path loss measurements in homes as well. And although this is relatively backbreaking work, crawling around underneath people's sinks and putting sensors, it was actually very useful in trying to understand the system in terms of the frequency, bandwidth, and so on that you can use this network. So I'm going to go through some of these really quickly. First, there's the frequency of operation. This power line coupling actually works best in the HF band, so between 3 and 30 megahertz. This is a wavelength of 10 to 100 meters. And the reason for this is because in this frequency band, the size of the power line infrastructure is actually roughly an efficient antenna. So it's in this band that the power lines more efficiently pick up or receive this coupling signal from the nodes. Also in this band, the power lines don't attenuate the signal very much. They work well as a transmission line. Now, operating in this 3 to 30 megahertz band has a number of limitations in terms of bandwidth. So if you look at the unlicensed ISM bands that Snoopy can use, we have only about 10 to 100 kilohertz of bandwidth compared to the tens to hundreds of megahertz of bandwidth that traditional wireless systems have. Now what this means is we can't divide our channel into subchannels. So all the sensors share the same channel. And again, they don't have receivers on them, so they can only transmit. So we have to use pure aloha, where each sensor just sends data as soon as they have it. And what this means is collisions can happen. So in order to minimize the probability that collisions will happen, we want to keep the transmit time as short as possible. So each node is occupying the channel as little as possible. We also need to vary the time between transmissions. So since a lot of these things happen on a schedule, we don't want a number of sensor nodes to end up on the same schedule and always collide. And then, like I said before, we can use multiple retransmissions to increase the probability that important data gets through, and use forward error correction, again, to increase the probability that data can be recovered if there is noise, for example. Now, another challenge is the antenna design. Because we're operating in this 3 to 30 megahertz range, an efficient antenna is on the order of 10 to 100 meters in size. So if you want to make a device that's this big, you're not going to have a very efficient antenna. And so I did a lot of work trying to make as efficient as we can a small, electrically small antenna. And so I actually built an engine that actually estimates the antenna parameters using electromagnetics theory. And then you can actually solve a constraint optimization problem for a certain size and shape of the node, and it will tell you what's the most ideal antenna, either with wire-wrapped antennas or PCB antennas. And the next thing is actually the transmitter itself. So because we're really interested in making this as low power as possible, we wanted to optimize the power consumption of the transmitter. So we actually partnered with an integrated circuit lab, an analog integrated circuit lab at UW, to produce this custom integrated circuit. And the advantage here of doing this in full custom analog is that we can reduce the stray capacitance and therefore reduce the power consumption. And so we could actually achieve whole home range with this sensor network while consuming only 65 microwatts of power while transmitting. So this is that 2 orders of magnitude lower power than some of the existing sensor networks. Now the last challenge here is in terms of the receiver design and this forward error correction. And this depends a lot on the channel itself. So because we're using the power line as this receiving antenna, we actually have some challenges in terms of the receiver design. And that is, this antenna was not designed to be an antenna, and it actually changes over time. So as people flip on light switches and things, the impedance of the power line changes. There's all kinds of noise sources on the power line because of appliances that we need to deal with. And this really affects the forward error correction. So we want to develop forward error correction that works well in this noisy environment, which is not a traditional additive white Gaussian noise or even Rayleigh fading channel. You actually have power bricks that are producing noise synchronous to 60 hertz. The noise floor changes largely all the time because of appliances. And trying to produce error correction codes that can handle this and make the system robust has been another focus of my thesis. Now, once we understand all these things, the next question is, what are the applications of Snoopy? Well, first, we need to consider the limitations. So, for one, it requires power lines. So this is not the sensor network to deploy in the Amazon. It won't work. It really needs to work indoors. So it's best for home and commercial applications. But like I said before, what's nice is this is actually a problem domain for traditional wireless sensor networks. So walls, traditionally attenuate wireless signals, and so they're typically a problem. In our case, walls are good because within the walls are those power lines that we need for our network. The other limitation is the low bandwidth that I talked about before. And because it's low bandwidth, this is not the sensor network to use for streaming media, audio or video. It's really for event detection and low rate monitoring. And in this application domain, we can actually achieve greater than 10-year battery life. And in fact, that 10-year figure is the limitation of coin cell batteries. So the shelf life of a coin cell battery is about 10 years. So the battery will actually corrode before we've pulled all the energy out of it. Now, because this works best for these low-rate indoor applications, it's really best for in-home monitoring. So home environmental sensing, smart home applications, and home security, where you can use these low-power, simple sensors like temperature, humidity, moisture, and so on to get an idea of what's happening inside the home. So, to enable these applications, some of my co-inventors and I created this startup company, Snoopy Technologies, in which we actually released our first product, Wally Home, about 3 or 4 weeks ago now. And so one of the nice things about this company, for the research point of view, is the large data set that we've achieved. So now we've deployed these things all over the US. This is not a map of where we've deployed Snoopy. This is actually just what it looks like from space. But we put them all over the US. We now have several hundred systems out there, and we've actually gotten a lot more data about what this noise looks like on the power lines in homes all over the place. And it's really informed a lot of the design in terms of how do we deal with this noise that we couldn't see in the 10 homes we tried in Seattle. So, in summary, Snoopy is this ultra-low power wireless sensor network. Let me actually pass around 2 of these. So this is the original research version of Snoopy. This is the commercialized Wall-E sensor node. I also have one of those Wall-Es that you can take apart. You can come up afterward and play with that if you want. There's also the receiver, but it's not packaged. You can look at that too. All right, so I've talked a little bit about some of my work with both on and off-body sensing. But looking forward, I want to continue to identify these new opportunities for sensing, build new embedded sensor systems, and then apply these sensing systems to new domains. And in particular, I've become very interested recently in a slightly different domain of on-body sensing, and that is the domain of health and wellness. So this is work that I did here last summer on continuous non-invasive hydration sensing, which Desney captured my excitement about hydration with this wonderful picture here on my last day of my internship last year. And the reason I've become really interested in hydration sensing lately is because there was this study last summer which actually showed that 75% of Americans are chronically dehydrated. And this is actually quite a shocking number. And what's even more surprising is if you actually look at the symptoms of chronic dehydration. So the symptoms are things like allergies, low energy, depression, hunger, and digestive problems. And so, these things are often masked as other things, but it often is caused by chronic dehydration. And one of the things that people don't understand is that a lot of the beverages they consume throughout the day actually dehydrate them more. So things that are loaded with caffeine, sugar, and alcohol actually have a dehydrating effect. So obviously it'd be very useful to have a device that monitors hydration. The problem is, right now the best way to do this is blood tests or urine tests. This is both invasive and cannot be done continuously. You could also imagine, tracking the flow. So they actually make these water bottles that tell you how much water you've been drinking. The problem is, to accurately monitor hydration, you need not just inflow, but also outflow. And this is actually quite difficult because there's a number of ways in which our bodies lose fluid throughout the day. So it would be very useful to have a sensor which continuously and non-invasively monitors hydration. So similar to some of my other work on body, I'm going to take advantage of the fact that the body is a conductor and use that to sense hydration. So the approach I'm taking is using bioimpedance analysis. So this is something that's been done in clinical practice for quite some time, but for a different application, for actually monitoring body composition. So you can actually buy a scale now that tells you not only how much you weigh, but what % body fat you have. And if you look at the clinical studies using this bioimpedance analysis, they say it works fairly well for this, assuming constant hydration. And so my hypothesis is that if we, instead of looking or taking these measurements, daily or a few times a month, we actually look on the time scale of minutes to hours, then changes in bioimpedance should be a function of changes in hydration rather than changes in body composition. So in order to test this, I built this large circuit which does this bioimpedance spectroscopy to monitor hydration throughout the day. And we've started doing some studies. This is my internship last year, where I would continuously monitor my bioimpedance throughout the day while very closely monitoring my hydration as well. And this is ongoing work, so I don't have any exciting results yet. But the idea is that we could make like a wrist-worn device, like an armband, that can continuously monitor hydration just for average consumers to get an idea of how dehydrated they are. We've also talked to some physicians about using this during surgery to monitor hydration, which is something they're very worried about during surgery, and right now they basically guess. And I think it would also be very useful for medical researchers to study chronic dehydration. So that 75% of Americans number is actually somewhat debated because they can't really measure chronic dehydration. So with a device like this, people could actually study chronic dehydration and learn, what are the effects of this. So, in addition to monitoring hydration, I want to continue to work in this space of continuous non-invasive health sensing. But I also plan on working on other applications of embedded sensor systems, including technologies for accessibility and improving healthcare in the developing world. So by continuing to identify, build, and apply some new embedded sensor systems, we can reduce these current adoption barriers and hopefully truly bring Ubicomp to life. And again, this requires not only doing more research in each of these subdomains, but doing multidisciplinary research that crosses the traditional boundaries between the human interface, the sensing, the computation, and the communications. And I hope to be able to collaborate closely with the experts sitting in this room, as I've done for the last several years, to help develop these sensing technologies of the future. So I'm going to thank everyone I've worked with, many of which are here, over the past few years on these projects, and open it up if you guys have any other questions. Thanks.
So I currently have a smartwatch in my office that does hydration sensing, but frankly, I don't think it does it very well. So I think it's just measuring, sort of ambient dryness in my skin or some such thing. Can you comment on sort of how accurate sort of your skill is?
Yeah, so what I'm doing is a little different. I'm not actually looking at the skin hydration. So by doing this bioimpedance analysis, and at the moment anyway, across a larger area of the arm, we're actually looking at the hydration inside the arm. And the other thing I'm doing is, instead of looking at a single frequency, by doing this bioimpedance spectroscopy and looking at cross frequencies, we can actually tease apart the difference between intercellular fluid and extracellular fluid. So it turns out, as you might know, hydration is actually rather complicated. There's no medical dehydration. What we really care about is the fluid in a number of different compartments inside the body, as well as the sodium and potassium concentrations. And by doing this continuous monitoring of both intercellular and extracellular fluid, we can also see the shifts in the fluid between those compartments, which can give us some idea of those ion concentrations as well. So I think with such a device, you could actually get a lot more medical relevant data about dehydration.
One of the issues in that realm is always the time it takes from replenishing and it showing up at some distant site.
Exactly.
So there's that lag.
And I think that's also something that it would be kind of interesting for the average everyday consumer to understand. Like when I drink, how long does it take before my body actually gets that hydration? Yeah.
Okay, you mentioned that you foresaw some applications of embedded sensors to accessibility. I was just wondering if you could expand a little.
Yeah,
further
so I mean,
on that.
if you look at kind of the HCI community in general right now, we've done a lot of interesting work on using hands-free interfaces and things like that. And I think it would be really interesting to take a lot of these technologies we've developed for HCI and move them into the accessibility realm, where the problem's a little different. Dealing with errors is a lot more difficult, and trying to actually take a lot of this new research and produce devices that can actually help in accessibility. So I haven't done too much kind of diving into that yet, but I kind of see there's this big potential there to enable a lot of technology for accessibility.
So you mean accessibility for people with motor impairments?
Could be motor.
Because your picture showed braille.
Yeah, it could. I mean, it could be vision as well. I mean, there's been a lot of work, in the community on eyes-free interfaces, and so can some of those be applied to accessibility? Is one big question. And the design constraints are different with blind users. So, yeah.
The microwattage power levels you were talking about for Snoopy, what's the bandwidth we're talking about? Like, what's
So-
the rough bandwidth ceiling at? You said something like 50 megawatts there.
Right. So the bandwidth, it depends on, you're partially limited legally by, unlicensed bands. But if you kind of ignore that, I would say it's around 100 kilohertz, 200 kilohertz, hundreds of kilohertz, basically.
Kilohertz? You mean I'm thinking in bits, like roughly you
Bulk.
I just said bulk, but I'm just trying to get what is the kind of data you can move over the wire. You know what I mean? Like.
Then I think
move a string every minute, like that. Like,
yeah, you could move a string every minute. So I think you're going to be more, I'd say, on the order of 1 kilobit per second.
That's pretty good. At 50 microwatts.
But if you were to do that, so the part of the problem is it depends on how many sensor nodes you have, right? So you could maybe have one that's doing that continuously, but if you have 10 of them, maybe you get a tenth of that rate for the network and so on. Yeah.
How, how effectively is your power line network able to jump between phases? Residential homes, it has 2 phases, and commercial, it has 3 phases.
So one of the nice things about the HF band, 3 to 30 megahertz, is that it actually couples quite well. So 3 doesn't couple quite so well, but basically above 10 megahertz couples very well across the phases. So that's actually not a problem. So a lot of the existing work on power line communication had that problem initially, like X10 for example, and they were using 125 kilohertz. And so that was their problem. The newer systems, like some of the new Insteon systems, actually use the same band, 3 to 30 megahertz, and they don't have that problem anymore.
Would there be a conflict between Insteon and Snoopy then?
So I mentioned the forward error correction, and all, because we're making a commercial product, a lot of the challenge is how do we make it work with Insteon, with these existing systems, and it does work actually quite well alongside that. There is more packet loss, but we handle it. Yeah.
But how far does it go?
Right, I mean, I remember as a kid, using X10 devices in my house to control my neighbor's house.
Well, in a home, it doesn't go very far because it typically doesn't make it through the meter. There's enough inductance typically in a meter that it doesn't couple across. It certainly, even if it does go through the meter, it won't make it across the pole top transformer. In an apartment building or a condo, then yes, it will. Your neighbors will see your signals as well.
So when you calculate your bandwidth, then you have to take into account all your neighbors.
They're part of the same network. Yeah, exactly.
Going once? Going twice? Thank you, sir.
So I have